So could you please tell us about who you are?
So my name's Kevin Shinpaugh. I'm a collegiate professor in the aerospace. Well, it's the what is it? The Kevin T. Crofton Aerospace Department at Virginia Tech.
Mhm. And why did you want to become an aerospace engineer?
Oh, see, I grew up when I was a kid. The Apollo moon landings were going on. So I was 5 years old when uh, Neil Armstrong and Buzz Aldrin landed on the moon. So I was into rockets, and that's what I wanted to do.
Mhm. And what are in Virginia Tech, you work a lot with different students and different student organizations. So what are some of the projects that you work on with students? And what are their purpose?
Yeah, so nowadays there's a lot of opportunities for students to do hands-on projects.
Mhm.
And these things are very valuable for the students because if you're looking at getting a job at SpaceX is, they don't care what you got in your courses. They care to some extent, but they want to know, what did you do hands-on? And so we give students a very good opportunity to do a lot of hands-on work. So some of the projects we have several rocketry projects. So one team's called Orbital Launch Vehicle Team. They're designing a rocket to send a 5 kilogram payload to the Von Karman line, which is 100 kilometers. We have another student team that does a yearly competition at Spaceport America, which is in New Mexico. And basically I think it's through the International Amateur Rocketry or Sounding Rocket Association or something like that. They have to build a rocket to take a payload to 10,000 feet, and they can either use a commercial motor or they can build their own. And so the student team this year will actually fly one with commercial motor, but they are in the process of building their own hybrid rocket engine. So it's going to use nitrous oxide and paraffin wax. So they're in the process of developing and testing that. We also had some robotics projects. So in the past, we had the students had built some NASA-related sponsored projects for robotics. So RoboOps was one. The students had to build a robot that went to Johnson Space Center in Houston. They had to control it from their primary university location. There's other students at Johnson, and they were in the Mars Rock Yard. And so they had to go around the Mars Rock Yard and collect colored rocks, which were kind of representing some of the science goals. And then there's some bonus points as well. Most recently, we did something called the Moon to Mars Ice Prospecting Challenge. This is where NASA has set up a simulated Mars environment on Earth. Basically, it's a big block of ice, and then they put various layers of regolith and other things. The students have to drill through this upper level material to get to the ice, melt ice, remove it, and purify it. And then, they get judged on how much they produce. So the goal is NASA's really looking at the students to come up with some other ideas that they may have not thought of that could be used on Mars.
Can you also explain what the Virginia Cube satellite constellation is and what the purpose was?
Yeah, sure. And I can probably pull up a photo here in a minute if you want. Give me a minute. So Virginia CubeSat constellation, this was a project that was funded through NASA, but it was a Virginia Space Grant, which is the consortium here, was the primary sponsor of that program. And then there is Virginia Tech, Old Dominion University, and also University of Virginia were participating in this, and we built 3 CubeSats that were supposed to operate as a constellation. And so the goal was to use this constellation to measure drag and to, basically give students hands-on experience building a CubeSat. If you want, I can share my screen, show you a photo of this real quick.
Go right ahead.
So this is a view of the CubeSat as it's being launched from the International Space Station.
Mhm.
This is the Virginia Tech CubeSat right here. What you see here is the solar panels on the International Space Station. And then these two CubeSats were the Old Dominion and University of Virginia CubeSats. And so the old U1 had a drag brake that was supposed to deploy. And we think it did deploy because its orbit is highly different than the other two CubeSats.
All right. And could you also explain what System X is?
Okay, so I actually wear two hats at Virginia Tech. So I do about 50% of my time in the aerospace department, and the other 50% of my time, I'm in this group called the Advanced Research Computing Group at Virginia Tech. So we run the supercomputers for researchers to use at Virginia Tech. So System X was our System 10. That was done in 2003. It was the third fastest supercomputer in the world in November of 2003. And so back then it was a $5 million project. We did it in about 3 months, which was, so if you looked at the other people on the list at that time, the one above us was a $30 million project. The one below us was a $30 million project. We did ours for 5 million, and we did it in a shorter period of time too. So it was a really cool project. So it was third fastest. It ran for about 10 years. So if you look at the total CPU cycles generated by the computer, it was the #1 supercomputer for the 2001 to 2010.
And what is Project Luna and what is Project Aurora?
Okay, so Project Luna. So there's this competition that NASA sponsors through the National Institute of Aerospace. Project Luna was one of their themes that they did. So basically, if you've heard of the Deep Space Gateway that NASA's planning on doing, this is a gateway that's going to be a very small space station that's going to be in orbit around the moon. So a halo orbit. So it's going to be very highly elliptical. The thought is that NASA wanted to see about using a space tug to take payloads that may be at the Deep Space Gateway and move them down towards the lunar surface. Now, the tug would just take them into low lunar orbit. And so I had a student team that did a design. They came up with an innovative design solution. NASA gave us a broad range. They said it was up to 15,000 kilograms payload. Well, the students were looking at it. Well, what if it's a smaller payload? Well, if you have a big system that's moving a small payload, you get a lot of inefficiencies. So what they did is they broke it off into two spacecraft, one which was mainly electric propulsion, and then another one that was chemical propulsion. So if you're moving the big 15,000 kilogram payload, you couple these two together. So basically one fit inside the other, and it would dock with the system and then move it down. If you have a very small payload, well, then take the smaller subsystem, the small payload, a lot higher inefficiency. And so then if you have two small payloads, you can use these two systems to independently move them.
Mhm.
And then Project Aurora. Project Aurora was one last year. So that was looking at sending a human mission to Ceres. So Ceres is the largest dwarf, I guess it's dwarf planet kind of asteroid. So it's got a lot of water, frozen surface. It's kind of and so how many AU is it? It's I think it's beyond the Mars of the orbit of Mars. And so it takes a lot of energy to get there. And so the students designed a human mission to take 4 astronauts to Ceres. And what they had to do was orbit Ceres for 30 days. And then they had to land the astronauts, 2 out of the astronauts onto the surface to do some various scientific investigations. What was unique about the team that Virginia Tech had, Most of them used a small propulsion. The Virginia Tech team looked at doing a tether-based system. So put yourself in the proper orbit so you can get a Ceres stationary orbit. And so your point above the surface is not changing, even though you're in orbit. And so they could drop a tether down with a module that would have the humans on it. So it'd take a while to get down there, but it's very low propulsion requirements. They could then, astronauts can be on the surface. They can then be brought up. They could reposition, go down again. So they could visit multiple sites on the surface of Ceres in a very short period of time with very little propulsion. They did have a propulsion system on board in case something happened with the tether, then they can return back to orbit and dock. So they got an award for most innovative concept.
Mhm. And with all these projects, there I assume there's a lot of like simulations and lots of design things that has to be tested. So what are some of the challenges concerning the creation and utilization of a proper testing ground for advanced space and vehicle probe concepts?
So the students who take my class, this is a senior design class, so it's for spacecraft. They have to go through something sort of like the system engineering process that NASA has developed. And so they have to understand what are the requirements, what is it they're trying to accomplish, what is the technology they can use. And so then they have to develop requirements. They have to look at additional requirements. They have to look at risk. And so they're trying to bring in various components that can operate together as a very large system. So like on the Ceres one, you have nuclear thermal rockets, you had fuel storage that you had to do, you had habitat that you had to do. You had all these systems that have to operate together. Now, of course, this was a paper-based design, but they still have to look into some of the stuff. Now, one of the things they did do is they have a lab component as part of this class. They looked at how they could look at the surface of Ceres. So they kind of simulated the surface of Ceres to see how they could attach their lander while they're on the surface, so it wouldn't drift away or something like that. So that was one of the things they looked at to testing. So what was the other part of your question there?
So what are some of the challenges in creating a proper testing ground for any of these?
So NASA does a lot of that. So I don't know if you've heard of HIAD.
Mhm.
HIAD is a hypersonic aeroinflatable decelerator.
Mhm.
So if you looked at the stuff we sent to Mars, they usually have a hard shell heat shield.
Mhm.
So they come in, they're using the heat shield to dissipate some of that energy and then eventually jettison the heat shield and then deploy chutes and et cetera, and eventually land on the surface.
Mhm.
When you look at sending humans to Mars, these things get very large. You're talking probably 5 to 8 meters in diameter
Mhm.
and probably around 20 metric tons. So if you're looking at doing a hard shell system, that gets very large. You'd probably have to have one that's probably maybe up to 10 to 30 meters in diameter.
Mhm.
If it's hard shell, how do you pack that into your spacecraft? So the idea is use an inflatable system instead. So it's this is the front of the spacecraft. It's all compressed down here. Just before Mars entry, you inflate it, and so it'll slow down the system. So what NASA's doing at the moment is they have a sequence of tests here in Earth environment to test this out. So one of the first ones they did was basically send a sounding rocket up. It gets up to maybe 1,000 kilometers or something, and then it comes back in. So it's probably coming in maybe around Mach 5 or something like that. So it's not simulating the true environment that it's going through, but it's doing something.
Mhm.
So they've done some tests like that. Most recently, they did one test where I think it was from a balloon. They get the balloon at the right altitude, and now they have a sounding rocket that's going to take this system at the altitude that really mimics the atmospheric pressure of Mars. So they can get that true more matching of what's really going to happen at Mars. And so they send this thing at Mach 5 and try to simulate that. At some point, they're probably going to do an orbital reentry test from maybe the moon or something like that. But again, you got to test some of this new technology, make sure it works before you put humans on board.
Mhm. Right. And what would you say has been your toughest accomplishment so far in your career?
I love doing student projects. I like working with students, being their mentor. So, again, I wear two hats. So the System 10 project was really a fantastic project because we did it in very little money, very little time, and it worked. And me and my team had never built a supercomputer in the world. I mean, built a supercomputer before. And to build a working supercomputer in 3 months that made the top 3 is just a fantastic accomplishment. The other thing is I'm proud of my students that do these competitions and do very well. So there was a few years ago, we did one, which was a human mission to Mars. And so my team broke it up into 2 phases. One was to deploy cargo under the surface of Mars, so it'd probably be the habitat and the Mars ascent vehicle. So they basically designed this craft, a very large spacecraft that could do this. It was using a fusion-driven rocket engine to get to Mars. So we don't have those yet. Maybe in a few years, maybe in 10 years, maybe in 20 years, we might. But they brought this, what they did is had this thing come into a trajectory that was free trajectory return back to Earth. And what it did is it dropped off the payload and used solid rockets or some other rockets to get this material into the Earth, into Mars's reentry pattern and land at the right spot. So then this big ship comes back, comes to Earth. The thing is, it's already been proven to do an interplanetary mission on that cargo mission. And so it's reduced the risk. Now they can put the humans on board and then send it back out. And this time it gets into a parking orbit. Mm-hmm. So they won first place in this competition, the Rascal competition, but they had some key elements that NASA really liked, and it changed the way NASA was planning their Mars missions. So the students had real impact on NASA's planning for Mars. And it wasn't the fusion-driven rocket, it was basically doing this hybrid propulsion where the deep space part is being done by one part, and then when you get to the planetary systems, you're using a different type of system. So in this case, NASA's now looking at electric propulsion in free space and chemical propulsion in the gravity wells of Mars and Earth.
Mm-hmm. And what is a big milestone that you're looking forward to in your research?
So we have another CubeSat going up in this coming year. It's going to be a 3U CubeSat. We're going to have multiple systems on there. One is a composite boom. So are you familiar with the solar sails that NASA's been talking about, or JAXA and stuff? So basically you deploy these very large booms that have a very, very lightweight, thin mylar system. And basically you're catching the solar light pressure and it's going to propel your spacecraft. Mm-hmm. So you need booms that are 40 meters long. And so NASA's developed this composite boom that you can roll up like a tape measure. And then when it's time, you just reel this thing out, and now you get a 40 meter long boom. And so we're testing a segment of that stuff, maybe about a meter long. We're going to test it on the CubeSat, see how it deploys, measure some of the vibrations and stuff like that. Within the next 10 years, I would like to do a student project where we send something to the moon. So I'd like to send, maybe a 5 kilogram to 50 kilogram project to drop onto the surface through the commercial lunar program system.
Right. And to To high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Oh, aerospace, I mean, it's challenging. You know, if you notice, I say I wear two hats. So when I graduated in 94 with my PhD, aerospace had, again, you get this cyclic thing in the aerospace market. So back in the 60s, we're doing Apollo. In the 70s, things kind of slacked off, and then they started shuttle program. Everything came back up. Then in the mid 90s, they started slacking off again. And so you had a lot of people that had to leave the aerospace firms and stuff like that. So when I graduated, there was no opportunity. So I kind of did a whole bunch of other things. I did some fiber optic sensors and other things like that. Again, now we're SpaceX and all that. So Blue Origin aerospace engineers are in high demand. At some point, that's probably going to change again. But if these commercial companies do really well, I think there's going to be a lot of demand, and it's different now. You know, from the 60s to probably about the mid 2000s, it was NASA, big government projects, etc. SpaceX has changed things. So now they're doing a lot of things in space that they want to do themselves, and they're finding the money to do. They are still getting government contracts, but they're able to do some of this stuff even without the government contracts. And so we're going to see a big change in stuff. And especially if we look at climate change, space, we're going to have to take advantage of space to try to mitigate this. You know, putting sensors and stuff in orbit is one part of it. And if we can move some of the manufacturing, our energy generation, or even materials that we can harvest from asteroids or manufacturing and stuff like that, space could be very lucrative and also can be help us in some of these problems. And so again, if you're wanting to do something in aerospace or space, you have to have a broad knowledge: computer science, electrical engineering, yes, system engineering, because everything requires electronics, everything requires programs now. So you have to have some of that understanding to really make these systems work.
Mhm.
Does that help?
Excuse me.
Yeah.
All right. Well, thank you for joining me, and thank you for letting me interview you. That was great.
Okay.